Hi, I'm Michele Chiari from Politecnico di Milano, and in this video I'm going to explain in more detail how we can model check context-free languages. So, first I'll introduce the problem. Then I'll give some background on operator precedence languages, or OPL, which are the subclass of context-free languages that we address in our work. Then I'll present precedence-oriented temporal logic, which is a new temporal logic that we introduced that has explicit modalities that interact with the context-free structure of words. Finally, I talk about how we applied this to the verification of procedural programs with exceptions. In short, model checking is the verification of a system model with respect to a requirement specification. The kind of properties that we can check depend both on the formalism that we use for the model and the one that we use for the specification. For the specification, one of the most popular ones are temporal logics, such as linear temporal logic or LTL. In the literature, more expressive kinds of temporal logics have been introduced, often with the aim of verifying certain specific domains. For example, logics based on visibly pushdown languages such as CaRet and NWTL were introduced for model checking procedural programs. But what's the advantage of using these more expressive logics? Well, it mostly lies in the algebraic structure that we use to reason on time. In LTL, we just have a linear order, which represents a linear succession of events. This is useful to express many properties such as reachability, safety, and liveness. But it's not enough for model checking certain properties of procedural programs. With logics based on visibly pushdown languages such as CaRet and NWTL, we have nested words. In nested words, in addition to the linear order, we also have a binary matching relation, which is useful to model program traces because one can match function calls with their respective returns. However, in modern procedural programs, we have behaviors that are more complex than that. For example, we have exceptions. In exceptions, we have a single event that terminates many function calls, and we would like to put all those calls in relation with the events that terminate them. But with nested words, we cannot, because the nesting relation is one-to-one. So we introduce OP words, which are based on operator precedence languages, and OP words have a nesting relation that can be many-to-one or one-to-many in addition to one-to-one. So we can model exceptions. As you can see, here we have an execution trace where all terminated calls are in relation with the exception that terminates them. We could also model continuations. However, in this talk, we focus on exceptions only. So now let's see what these operator precedence languages are. Operator precedence languages, or OPLs, were introduced by Robert Floyd in the 60s with the goal of efficient parsing. But they also have some other interesting properties, because they form a Boolean algebra, so they are closed by union, intersection, and complement. They are also closed by concatenation and clean star, and containment is decidable. Since, of course, emptiness is also decidable, they are ideal for model checking, where these closure properties are needed. And so we try to use them. In OPLs, the context-free structure of a word is embedded in its terminal symbols by means of three precedence relations, which were inspired to precedence between arithmetic operators. For example, times takes precedence on plus, and so on. So we fix an alphabet and the relation between all pairs of terminal symbols. The precedence relations are called yield precedence, equals in precedence, and takes precedence. They can be seen as generalized parentheses. Yields precedence is an open parenthesis, while takes precedence is a closed parenthesis that can match one or more open parentheses. So now we see what these relations mean in practice when we parse a word. So we fix an operator precedence matrix here on the right, and this one allows us to represent traces of procedural programs with exceptions. So we can have function calls and returns. We can have exceptions, which are raised by the functions, and also handler, which are installed by functions that catch exceptions. An exception terminates all the function calls that it finds in the stack before it finds a handler. Here we also have a word, which is a stack trace of a program. So the first position is a call, which returns normally at the end. This call installs an exception handler. Inside this handler, two other calls are made. The first one makes the second one, and the second one raises an exception, which terminates the two functions until it is caught by the handler. The initial function then makes another call which returns, and then it returns. And the precedence relations allow us to parse a string so as to get its context-free structure and build its syntax tree. We generate our nesting relation, which we call the chain relation, by doing parsing. So let's see how to do that. First, we highlight all precedence relations between consecutive terminal characters. Then we match all patterns of this form. So we have a terminal symbol that yields precedence to another one that may be equal in precedence to some other terminal symbols, and the last one takes precedence from the next one. So here, for example, we have the second call that yields precedence to the third one that takes precedence from the exception. And the two tokens, the two terminal symbols around the third call are called the context of a chain. So this whole structure is called a chain. And the internal call, so the third call, is the body of this chain. In a parsing setting, each chain body corresponds to the expansion of a non-terminal symbol. So we reduce all the chain bodies. Now we reproduce the same procedure. So this time the handler yields precedence to the second call, which takes precedence from the exception. So as you can see, we now ignore this chain body, so the call that we removed. And we link the context, so the surrounding characters, with our chain relation. So now we can go on. The first call yields precedence to the handler, which is equal in precedence to the exception, which takes precedence from the next call. So here, as you can see, we have an equal in precedence, which means that both the handler and the exception are part of the same chain body. And again, we reduce it. So as you can see, we get our matching relation by linking all the chain contexts. And this relation is can be many to one. So the handler and the call are both in the relation with the exception. And it's also meaningful. So calls are in relation with the event that terminates them. So for example, an exception or a return. And also handlers are in the chain relation with the exception that they catch. So we can go on, and here on the right you can see the syntax tree of our word, where we highlighted precedence relation either between consecutive characters and characters linked by the chain relation. All the dots that you see here are internal nodes, and they are non-terminal symbols in a parsing setting. As you can see, they are anonymous and they are transparent during parsing. And that's why our nesting relation links them. So basically, the chain relation augments the linear order by considering non-terminals as if they were non-existent, as if their expansion wasn't there, and so they can be skipped. So according to the chain relation, terminals that are separated by just one non-terminal are as if they were consecutive. So if we look at the precedence relations between tokens in the chain relation, we can see that those that are in the equals in precedence relation form one-to-one relations. Those that are in the yields precedence relation form one-to-many relations. So, for example, if you look at the call in position 1, it's matched with the handler, and the call in position 7 by the yields precedence relation. And also positions in the takes precedence relations form a many-to-one chain. And as you can see, the meaning of this structure is related to the meaning that we have in our context. So each call and return pair contains all of the other function calls, handlers, and exceptions that occur during that function call, and also handler and exception pairs contains all the function calls that are protected by that handler. So now let's see what this new temporal logic that we introduced looks like. We called it precedence-oriented temporal logic, or POTL, and it is based on OP words, which, as we just saw, combine the linear time with a binary nesting relation that can be many-to-one or one-to-many, besides, of course, one-to-one. POTL has future and past modalities that can go back and forth in time, but also up and down on the syntax tree. And we prove that POTL is equivalent to first-order logic with one free variables on OP words, and consequently it subsumes LTL and also the logics based on nested words, so it's just CaRet and NWTL, and also OPTL, which is another logic based on operator precedence languages. So let's see the syntax and semantics of this logic. So CaRet introduced the idea of jumping over function bodies. Here we bring this idea further, we generalize it also to the one-to-many and many-to-one relation cases. So we have next and back operators that are the ones with the little circle, and chain next and back operators, which are the one with the chi. And the normal next and back operators go back and forth along the linear order. And as you can see, there's a D on them, which means that this variant goes only down in the syntax tree. There is also a variant with a U, which goes up, which is symmetric, but here we see only the downward variant. So if we take the linear next, for example, we can evaluate it in position 1, and as you can see, it evaluates psi, so its argument, in position 2. And as you can see from the syntax tree, position 2 is down with respect to the call in position 1. We also have the chain next and back operators that go back and forth along the chain relation, of course. They are both combined in downward summary paths. So these kind of paths can both go along the linear order and the chain relation. And the downward variant only goes down in the syntax tree. So here, if we evaluate this formula, so true until down PC, and we start from position 1, we have a path that goes then to position 2, to position 3, and to position 4 and 5. And as you can see, it always goes along the linear order, and it also goes down in the syntax tree. So since from position 1 to 4, true of course holds, and in position 5, PC holds, so that's a call to procedure C, then this operator is true in position 1. And notice that while we go down in the syntax tree, we are also going up in the program stack. So if you consider the state of the program stack in position 5, you can see that there is a call to PA at the bottom, and then the handler that it installs, and then 3 more calls, 1 to PB and 2 to PC. And as I said, we can also jump over chain bodies by going along the chain relation. So here we evaluate in position 1 this true until down return. So since there is no return from position 2 to 6, we jump over all of that by following the chain relation between the call in position 1 and the one in position 7. As you can see, we are also going down in the syntax tree, and if we consider the stack in position 7, the exception has already been caught by the handler, and so the only thing that is in the stack besides the call to position 7 is the call to position 1. So as you can see, this kind of paths go along the stack contents in any position. And we also go on with the linear edge, so we reach the return, and this operator is true in position 1 because of the path that is made of position 1, 7, and 8. And we can use these kinds of operators to express properties that are called stack inspection. So here you see a formula. The leader square is an LTL globally. And so it means that its argument is true in all future positions. And it says that whenever we have a call to function PC, then true since down handler must be true. So since we have downward path, if we go backwards in a downward path, we actually go up. So we start in position 5 because it's a call to PC, and we see what's in the stack in that moment in time from top to bottom. So if we go on, we see that there's another call to PC, there's another call to PB, and finally there's a handler. So this formula is actually true in position, so true since down handler is true in position 5. And so the whole formula is true. So we can use this kind of formulas to see what's in the stack in a given moment in time. Since we have one-to-many and many-to-one relations here, we also would like to move along the many positions that are in the chain relation with a single one. So for example, here we have the calls in position 3, 4, and 7, which are all in the chain relation with the exception that terminates them, which is in position 9. So we would like to move along these calls without taking into account what happens between them. And for this, we use hierarchical paths, which move along positions in the chain relation with the same position. So we have the hierarchical next and back operators, which go just back and forth for one position. So, for example, in position 3, we have a call to procedure B, and in position 4, we have a call to procedure C. They are both terminated by the same exception. So in position 3, hierarchical next down PC holds. As you can see, we are still going down in the syntax tree, so from position 3 to position 4, and they are both in the chain relation with the exception that terminates both of them. We can also have an until operator or a since operator on them, so we can have call hierarchical until down PE. So we start from position 3, we go to position 4, then we jump all the way to position 7. And we can do this because positions 6 and 5 are not in the chain relation with position 9. So in position 3, we have a path made of position 3, 4, and 7. And in position 7, we have PE. In the other positions, call holds. And so in position 3, this operator is true. This can be used to express very complex properties on calls that are terminated by the same exceptions. So here, for example, we have again globally PE, and this is a chain next up. So if the current position where PE holds is in the chain relation with an exception, so which basically means that the current position is a call terminated by an exception and it's a call to PE, procedure E, then we have two hierarchical since operators, one inside each other, so we can concatenate them. They are compositional, and what they say is that if procedure E is terminated by an exception, which is the left-hand side of the implication, then the same exception also terminates PC and PB, so procedure C and B, and in the meantime it does not terminate PA. So here we have in position 6, we start with this path where P holds, and then as we go on until we find PC, and we go on between position terminated by the exception in position 8. PA does not hold in any of these, and finally we reach PB. So this formula holds. So let's see how we used POTL to model check procedural programs. So we gave an automata-based model checking procedure for POTL, and we implemented it in an explicit state model checker, which we called POMC. POMC accepts as models both OPA, or Operator Precedence Automata, which are the class of automata that characterizes Operator Precedence Languages, and also in a domain-specific language that allows to model procedural programs with exceptions and Boolean variable. The DSL is not in the paper, but you can find it in the artifact. So how did we model programs with OPA? Well, OPA are a kind of push-down automata whose moves are determined by precedence relations between consecutive characters. So if they find yields precedence, then they do a push move where they push a symbol on the stack. If they find equals in precedence, then they update the topmost symbol on the stack, doing a shift move. If they find takes precedence, then they pop one or more symbols from the stack. And there's a way, which we show in the paper, to implement OPAs that mimic the behavior of actual procedural programs. So we have 3 case studies. The first one is with 3 simple procedural programs, and the property that we check is that whenever procedure B is called and procedure A is on the stack, an exception is thrown. As you can see, we check this property very quickly. We also have a case study where we have a small banking application in Java taken from a paper. Here in the application we have users that have authorizations, and they can withdraw money or check their account balance, but only if they have the appropriate read and write authorizations. If they don't, then an exception is thrown. And we check whether anytime an unauthorized access is made, an exception is actually thrown to prevent it. And we model this both manually and with the DSL, and you can find the DSL one in the artifact, and as you can see, the time it takes is always quite small. We also have a case study on an implementation of a generic stack taken from a popular tutorial on C++, and we check that it is exception safe and exception neutral. Exception safe means that in all the operation on this stack implementation, if an exception is thrown, then the object remains in a valid state. Exception neutrality means that whenever an exception is thrown in one of these operations, then it is propagated outside and never blocked. And we have an implementation that abides to these properties, and one that is not safe. We modeled both manually and automatically, and as you can see, they can be checked in a very short time. We also checked 34 formulas to check all possible combinations of POTL operators, and as you can see, it takes a very small time and memory to check them. We only have one outlier that goes out of memory. So to conclude, we presented this new temporal logic and also a tool to model check it. In the future, we would like to apply this to actual programs, and we would have to develop abstractions to do that, and also explore more efficient ways of doing model checking, such as bounded model checking. So thank you for your attention and for watching this video, and please check out our paper and our artifact.